So we introduced different machineries consisting of this toPSAil, right? We talked about the anatomy of packbed, how packbed is modeled as a series of CSTRs, and how we can write mass balance equations and energy balance equations, as well as momentum balance equations for the empirical relation for calculating volumetric flow rates, as well as our constant axial pressure uh, flow-driven model formulations. So actually there's a bunch of things we can do with these, right? First of all, we can simulate single adsorbers Garson PSA cycle, as we mentioned. But also we can actually simulate the interaction between two different adsorption columns, and that's actually more interesting in terms of industrial applications. At least you need one pair of, two different adsorption columns so that they can interact with each other, such as do something like pressure equalization, which actually saves a lot of materials and boosts the recovery, right? That's one aspect that toPSAil allows, is we can simulate up to two adsorption columns and model the interaction, which are show the flow diagram here. So basically, this is the process flow diagram for toPSAil. So you are able to see that there's adsorption column 1 and 2, and then different feed tank, and the extract product tank and raffinate product tank, and then all these different valve configurations as well as the flow streams are modeled in our flow sheet. So this is what the toPSAil simulation is based off of. So going back to the different types of specialization of CSTR in series model. So CIS stands for CSTR in series, if I haven't made that clear again. So the number of adsorption column is something that we can change. And of course we can consider different steps, right? So high pressure feed and low pressure purge, those are kind of steps that either remain at constant pressure or relatively constant pressure, right? So we call them constant pressure steps, but depressurization and repressurizations are pressure changing steps because the pressure inside the packbed changes significantly during the step. So we can make that distinction, right? Pressure changing steps and constant pressure steps. Of course, we can simulate isothermal and non-isothermal operations, right? So the advantage of isothermal simulation is that the model is simpler and requires less parameters. Of course, it might not be a good assumption based on different adsorbent-adsorbate systems, because sometimes the heat of adsorption can be quite significant and we need to take account for that. And only when we need to take account for that, we can actually use the non-isothermal operation, right? But typical isothermal operation is much easier simulation to run. And we did talk about the distinction between axial pressure drop, right? So when we have the pressure-driven simulation using empirical equation like Argon and Kozenik-Harman equations, we're able to model axial pressure drop. And sometimes we need to, especially for industrial scale, larger scale adsorbers, right? But sometimes when lab scale, tall and skinny columns, the pressure drop is insignificant, so we don't need to do that. So then no pressure drop model or our flow-driven model can be used in that case. Of course, we have different multitude of the boundary conditions that are applicable, right? So we have things like linear valves that models the flow between the two different adjacent CSTRs, or even with the environment or the boundaries at the top, at the boundary of these columns, right? So there can be linear valve and then pressure downstream and upstream, or similarly linear valve pressure upstream and downstream. In this case, pressure in the downstream is higher, so it's flowing up. In this case, pressure in the downstream is lower, so it's flowing out, right? So we can model different types of flow with linear valve equations, especially as boundary conditions for these adsorption columns towards the end of the CSTRs, right? Because when we take a look at the CIS model, we need to provide the boundary conditions, right, in order to have the square system. In other words, what's the flow rate between the first CSTR and this bottom? What could be the downstream of this first CSTR? It could be something like a feed tank, or it could even be something like extract tank, or something maybe like environment you're just purging out. Similarly, you can have raffinate tank, or just venting out to the atmosphere as well. So you can consider different types of scenarios and those are modeled by different types of boundary conditions. And these boundary conditions include constant flow as well, close, obviously, no flows. Check valve, you can have check valve, which it basically picks the minimum or maximum flow rates depending on which end you're talking about. And back pressure regulator is there, as well as the combination of the check valve as well as the back pressure regulator. And then there's actually constant pressure boundary condition, which is used for the constant pressure motors, right?